We first show you a demo of dynamic RAN energy saving provided by the programmable RAN platform. Reducing the RAN's energy consumption is crucial both to improve sustainability and to reduce RAN operating expenditure. Our controller scales the RAN server's CPU frequency in real time depending on the traffic load, which saves energy even during peak times. When the network has even a short period of low traffic, our controller detects it and reduces CPU frequency to save power. As soon as a burst of traffic arrives, our controller adjusts the server to the new demand by increasing CPU frequency. As soon as the burst is over, our controller reduces CPU frequency again. Let us watch a short demo. Initially, we start the energy controller, which brings down the server power from around 280 watts to around 180 watts. The server stays at low power while there is no traffic, or when the load is low, like during this ping test. Next, we start a high bandwidth iPerf workload. Our controller now determines that this large amount of traffic requires high frequency, and we can see the server's power draw jump to 300 watts. While doing this transition, our controller ensures that it increases the CPU frequency before it admits the higher UE load. In fact, our controller can adapt the server's power in real time depending on the traffic. In this graph, we are showing the server's power draw for 3 different long TCP flows. Despite TCP's constant bitrate, our controller still saves energy during the millisecond scale low load durations that happen naturally when a TCP flow waits for acknowledgements. Next, we will show you how programmable RAN platform can help detect external wireless interference. External wireless interference can significantly impact network performance. In this demo, we can see the effects on the network throughput of an interferer that is active every 20 seconds. Detecting such interference requires specialized hardware and a truck roll. Programmable RAN platform can turn 5G RAN into a spectrum analyzer. It can detect interference in a live 5G network in presence of 5G traffic. It gives a network operator the ability to visualize spectral and temporal shape of the interferer on a single pane of glass and integrate in other operational processes. Next, we show you a demo of the RAN resilience functionality for RAN live migration and failover. It is designed as a platform service based on Open RAN interfaces. In today's vRAN, each radio is statically and inelastically mapped to one RAN server. Our platform exposes these as an elastic compute resource pool by dynamically changing the radio-to-server mapping. If we need to upgrade or failover the RAN, we can prevent user disruption by dynamically remapping its radios to a different server. Similarly, we can dynamically balance the load from RUs among the pool of vRAN servers for better resource efficiency. We can also power off some servers during times of low load like nighttime to save energy. The servers can also be powered off for servicing and maintenance. Our system provides resilience for the real-time DU component of the RAN running in a far edge. In our setup, the Layer 1 network function is from Intel, and we use the remaining DU and CU layers from Capgemini. Our system introduces a novel controller component that uses dynamic service models to install control and telemetry logic into the CU and the DU. This allows the system to intelligently combine IQ samples from different DUs to seamlessly migrate UEs from one cell to another. Initially, the UE is attached to DU1. As shown in the phone screen capture on the right, the UE is receiving data at 20 megabits per second. We next trigger live migration from our controller to move the UE's processing to DU2, which is running a newer version of the DU software with a different physical cell ID. The controller leverages the dynamic service models to intelligently combine IQ samples from the two DUs to perform a seamless handover of the UE's state from DU1 to DU2. We can see the UE's physical cell ID changes from 11 to 51, and that the UE's throughput remains completely unaffected during the migration. Next, let us see a demo of RAN failover. Here the UE is running video conferencing using a Teams call, where my colleague is waving his hand to highlight any disruptions in the call. When DU1 fails, which can happen due to a hardware or software crash, our RAN controller detects this failure in real time. The controller reroutes the fronthaul link as well as the CU-DU link towards a backup DU2. The CU reinstalls the UE state in the backup DU, and UE quickly reconnects to the RAN without a call drop. We can see that there is a negligible disruption of under half a second in the Teams call. Thank you for watching.